So, okay, we're going to talk about something like relatively simple. So we'll talk about filters. So image filters. How many of you have taken a class on cell processing, DSP, that kind of stuff? Oh, most of you guys. So you guys should be familiar with filters. For the rest of you, it's fine as well. You don't actually need that. Need to know what's filter to begin with, but if you already taken some of these classes, it's good to see the connection you have with image processing. Of course, what I'm talking about, this is more like classic image processing you can think of. And so first of all, okay, this is forget about it. I just massage the order completely. So let me just start with okay, think of what's filter. So as the name suggests, basically what filter means is just it's like water filter or air filters, right? You have something, you want to filter out something, right? So I guess the original meaning is you have some signal, or in this case some image or video. Typically you have noise there, and you want to filter out those noise. And in practice, we can generalize this idea a little bit more. So essentially you can just think of it as processing, that you have an image coming in, after some process you have an image coming out again. So for example, when we mentioned the first example, that to filter out some noise, it will be kind of like an application for enhancing images, there's image enhancement, and it can also be used in super resolution, in painting, and so on. And you can also use filter to extract useful information. We will talk about that maybe later on, not this class. We focus on the first one. So extract useful information, for example, the edges, corners, and block example. And also you can even consider transform, for example, Fourier transform, as some kind of filtering as well. And we'll also we'll talk about that later on, probably not in this class. So then first of all, to think of filter, as I mentioned, you can think of filter as just some operation, right? So if you have taken some class in signal processing, I guess the most important idea, maybe I'll just skip way ahead. Or this is some example, for example, I just mentioned some application. Denoising, you filter out some noise, right? This is the classic case, when you think of filter, it's okay, I filter out some noise. Or you can use that for super resolution, it'll be a lower resolution. And somehow with this process, you can make it higher resolution. And honestly though, filtering is not the state of the art for this kind of application though. For super resolution, probably if you use some neural network approach, you will get better performance. And you can also use do in painting. Also, in painting, probably in painting is like this. You have some, for example, watermark on an image. You want to just extract or just remove that. And again, filtering won't be the best approach for in painting also, but theoretically you can do that with filtering. So let's just start with a very simple example. Okay, let's see if I can move this thing around. This is a little bit annoying. I think I can move it. Okay, I can move it here. So so just think of a box filter. So I'm not sure you guys can just I mean, understand this notation here, so anyone have recognize what I'm writing? I just want to make sure. What's this symbol mean? Yeah, that's good. I have no idea what you guys learn, because I have no idea what. Yeah, so basically, this is what we're writing is just saying that okay, a box filter is for each pixel, instead of I'm going to I will replace basically a target pixel as the average over a rectangular neighborhood of that pixel. In this case, will be the 3x3 neighborhood. So therefore, this is 9 pixels. Actually, I'm a little bit sloppy here. Since I say n-1 and n-1, I should be should be over m by n, something like that. I'm not sure I can change that. append to not. This is not a equation. I'll change that later on. Let's see. Pointer, pen. I guess I can get a pen here. I mean, like in this case, it would be like, oh, actually, no. Wait, this is okay. Like n minus one, m plus one. So I'm summing over like, so for the current pixel nm here. So this is like pixel nm here. So I'm basically sum over my neighborhood, like, and take the average of them. Just sum over all of them and take the average. Or like I should say, just take the average of all of them and as the output. So this is a simple box filter. And I heard the toaster guys connected. So you guys can see the screen? Cannot hear response, but I assume yes. So okay. Okay, actually I have a drawing here, so I don't need that. So this is like, so yeah, let's continue first. Like, so this is give a more concrete example. Let's say, I'm not sure whether you guys can see that. Maybe I have a starting image like this very simple image. Like all these dark pixels have values is equal to 0. So it's just a grayscale image, have only one channel here. So, and this like white one is I have intensity equal to 90 or values equal to 90. So if I going to do a filter, so for this one, I add up the neighborhood will be just 0, right? Or the average will be 0. And this guy, the average will be 90, right? So sum of them over 9, and so on and so forth. So.
What about for the edges? You just can skip the edges?
Yeah, actually the edges, typically there's several ways we can do it. Like, one way, very simple, is just pad the edges with zeros. And then I just assume the edges is 0. Or you can do some reflection, like if this value is 10, maybe I put 10 here, like just assume the boundary just, yeah. So, but yeah, padding 0 is very typical. Actually, you can just think, okay, pad 0 and.
So this
yeah.
This is edge blurring or other edges, right?
This will be like kind of an effect of blurring. So with this box filter, because you take the average, right? So if you do a cell processing before, it will be like some kind of low pass filter. So you get kind of the image gets moving out. And so this is a very simple filter. So, and what was the value here? Just want to make sure you guys are following me. So after filtering, yes, this will be just 50, yeah, and so on and so forth. So this will be the filter image. This is the original image. So as he mentioned already, this is basically just smoothing effect, right? So remove some sharp features. And so this is another example. If you look at that, like if I have an image that I apply this box filter, it will be just like smoothing out like this. But you can see some artifact here, right? You can see some yeah, it doesn't look very nice. So later on we'll look at like some other filters will be a little bit nicer than this one. But this of course is like probably the simplest filters you can think of. Now let's see. This is basically repeating what I just said. Okay, now let's get into a little bit related to cell processing. Like if you think of like what we learn in cell processing, like one very important class of filter would be linear filters, right? This is just a reminder of you guys, like what do we mean by linear filters? So linear filters will be meaning that like if you have two images, weighted sum together, and you filter that, will be basically equal to the weighted sum of the filter images. So therefore it will be like this, right? This will be weighted sum of input, and then like will be just equal to the filter of each of these individual input, and then weighted sum together. It will be a linear filter. Just to check your understanding again, like so there's some property. So if a filter is linear, so is that additive? This is a definition of additive. Like is a filter addictive if it's linear? Huh? Yeah, because I can just put alpha and beta equal to 1, right? Yeah, so if it's linear, it automatically implies additive. I hate this, I cannot control Z. So I can write something like that. So how about like this another definition, so-called homogeneous. So I always don't remember what homogeneous means, honestly. So but this is like something like, I guess the definition more or less comes from like when you describe polynomials. So when you describe polynomials, for example, like fxy is equal to xy plus x squared, something like that. Then this is kind of homogeneous because like if you change the input from x to ax, y to ay, what you get like your output will be like something like a squared, like fxy, something like that. So you only have this nice property when like all your terms here have the same kind of total degree, right? So this is kind of similar to this kind of definition here, even though it's not identical. Basically, like if you have an image, you scale that, it will be just equal to the scale of the filter image. So again, like simple check of your understanding, like if it's linear, is that homogeneous? Yeah, we can set beta to 0, right? Yes. And how about, oops, let me, if I can erase all this. Erase, okay. So how about like stable? Stable meaning that like if our input is like bounded by something, then the output is also bounded by something. Yeah. It should be stable as well, right? It's hard to show actually. Here it's like a little bit hard to show. Why is stable? I don't know how to show it honestly.
Well, because if you have like a function, so we have a domain and we have a function.
Yeah.
So first of all, like the website part is saying that our domain is bounded, like it's not infinity. And from the first definition of linearity, if we have a bound domain, then we will have a bound function at the end, which means that if the domain is finite, then we'll have like a finite answer at the end. So it's not gonna like blow up at minus infinity or plus infinity.
You mean you're using the first one or like first property?
No,
the
I'm
second?
talking about like using the very first like equation on top. Yeah.
Bounded input, bounded output.
Yeah.
So whatever your function is, it doesn't go to infinity.
I don't know. Now I'm getting too dumb. I don't actually see the proof that immediately. So let's say I have f. I need to assume this way. I assume this is bounded input. So how can I use this to say like this would be like bounded output as well? So I mean like this is basically a definition, right?
Yeah.
So I should be starting with something assuming this is true. Then I'm going to need to use this somehow to show that. Of course, like this, when I say G is meaning that like S F and M, like S F and M should be less than CK somehow. Let's see, how can I show this?
It's absolute value, so the left side is above 0, and the right side is a value, not infinity.
You cannot just say this is 0, right? How can? I mean, like this is what you are given here. So you start with basically this is only two conditions, right? You have this and you have this. And then like if you want to really show this, you're supposed to use this, and then like, you want to argue that like this is true for some C, right?
Can't you just say like the action of S on alpha times F, your function?
Yeah.
Can't you just say that is going to be less than or equal to alpha K? and you say the same thing, or similarly for
Well,
beta.
this has to do with like the definition of the functions or like or the filter itself. So we know that most of the filters are tensor functions, and the tensor functions must be differentiable, which means that if you add like numbers small to the number you're looking for, you will not have very like strong perturbations in your answer. So given that, and given that you're not like using infinite bounds, like you're not using infinite inputs to your tensor function, you should not get a very like unbounded solution. So it has to do with if we know the definition of what f or what the tensor function s is. And
Oh, yeah, but then you will assume that like
yeah,
this has to be some tensor function as you mentioned, right?
yeah.
Then I need to prove that this is some tensor function given that it's linear. That's it's okay. Like I mean like I know it's true because I know for linear system like, but I forgot to prove that if your filter is linear, essentially like your this will be just equal to a convolution of your. We'll talk about convolution later on. So if the filter is linear, and also we need additional things actually. If this is also like shift invariant, then basically it's just a convolution. So because it's a convolution, therefore it will be stable. But just from here, it's actually, I think maybe can use the homogeneous property somewhere, but I'm not 100% sure. But it's okay. This is not, we are doing convolution, not doing math. So, but you just want to aware that like, okay, be careful. Like, I guess like for you guys when you, especially graduate school, like later on, like if you want to write some paper, then you need to write some proof, then you need to make sure that your proof will be kind of rigorous. So then like, so but anyway, let's continue with one more, just last thing. So how about invertible? Is that invertible?
It should be this linear, shouldn't
Because along with being stable.
Yeah, be careful. Not exactly. I don't think because okay. Think of the trivial. Yeah. What?
it? I think it's convertible if it doesn't have poles.
It doesn't have holes.
Poles.
Poles.
Yeah.
Oh, okay.
We have to look at the response.
Yes. Yeah. So this is so therefore it depends because as you said, like, I can give a very simple example like if it's poles or zeros actually. Because if my filter is just equal to zero filters, then of course it's not invertible. Because I can create something like stable filters, my output is just equal to a zero image. That thing definitely is linear. All I mean is that I have SF and M is just equal to 0. You can check that this of course is linear. So, but then of course it's not invertible. You set something equal to 0, there's no way you can recover that. So. But just some, but it's good. I guess it's a good exercise. So just remind you guys what is linear. Linear is important. And then this is another exercise. Just say, now think of like. Actually, this is I'm jumping ahead. I don't know. This is a little bit weird. So the way we think of like that box filter, you can think of like just doing a. Kind of like a dot product of a patch over your image, right? Is that right? Like I can think of like I'm doing this. Oops. Again, I cannot Control C this. What I mean is I go back to this box filter. What I mean when I say the box filter is equal to averaging over the neighborhoods of that target pixel, I can think of like this is equal to the operation is basically I have the image, actually this is even better if I go back to that, this one here. So I can think of it basically I have this guy here and apply a inner product of this with this neighborhood here, right? So inner product meaning that like for each element, I would just multiply this to this and add this to this and so on and so forth, right? So if you think of that this way, then I can generalize like filters, I replace different filters basically. I can, instead of box filter, it looks like this. I can have like different kind of filter. For example, I can have, instead of like all ones here, maybe I can have 1 0 0 1 0 1 0. Right, this can be another filter. For example, basically I'm just doing is again like, oh, take a patch here. If I want to compute the values of the output at this position, we'll be just doing like this patch and dot product with this guy. So okay, just make sure like you guys following me. Then okay, then again like some check of understanding, like how about this? Like if I have a patch like this, what is the output for this? I have an image like this, I have a filter, just this.
Still divided by 9?
No,
Okay.
no, that's not
So there's
divided.
no change.
Yeah, there's no change, right? Okay, yeah, that's definitely no change. So how about this? Yes, just shift it by 1 pixel. And how about this?
That way, so all the places shifted to like that, and then like to
Wrap around?
Oh, okay, let me give you a hint here. You can think of this like doing two operations. So like this. This first, and then do another filter in this direction, like let's see, 1 0 minus 1. Because like this multiplied by this 2 is just equal to this, right? You can think of really this is we're doing these two operations separately.
or we should do the right, and then it will be shifted like up.
Wait, that's one more. It's different from the last one here. This is only have 1 1 here, but here we have like 1 on both sides, and also 1 positive, 1 negative. Okay. This is like some kind of, this is actually first this guy here. This is similar to the box filter, but you see like the, of course I didn't divide by everything. Actually, this is similar to a low pass filter. So you can kind of like along the vertical direction, you're kind of smoothing the pixels a little bit. And this is a little bit like a high pass. So you think of like if I have, for example, if I have an image, let me just create some pixels here, write some pixels. For example, I have 10, 10, 10, 0, 0, 0, 0, 0, oops, 0, oops. I don't know why it happens like this. So apparently this looks like an edge, right? This is like looks like a vertical edge. Like if you think of this as an image, this is like on this side is a little bit bright here, and then this is like dark here. So it's like there's an edge, like a vertical edge. So if you apply this to this one here, so maybe I put more 0 here. So for this guy here will be just 0, right? So because this 2 is just 0, 0 or whatever. Like, but at here, basically you have like minus 10, something like. And then you move to here, this will be again minus 10. But let's say if I have more 10 here, then move to here, I will get 0 again. So what you do is it is basically kind of like have a high response point when there's a big transition, and when there's basic 0 response when the signal is moved there. So therefore it looks like it's kind of like a high pass filter along that direction. So therefore, oops, it's kind of ugly, but this is like what you get. So therefore, So as you can see, like it's not clear because I basically just detect all the vertical edges. So the high-pass filter along this horizontal direction will catch all the vertical edges, but it will just omit all the horizontal edges. So for example, the edges here, it will miss that. And so of course this will be like just the opposite, right? This will be like trying to do a low pass horizontally, then like a high pass vertically. So this time we catch all the horizontal edges and miss all the vertical edges. So is that clear? So I actually okay. One more. I don't know whether I should ask you this, but okay, maybe later on. So this is another one. How about this? Close. Yeah, there's a smoother here, but you subtract the smoother version. Yes, this is an interesting operation. They have a name for that. It's a unsharp masking, and yeah, the name is weird to me. I don't know. Like my English is bad. I don't know why it gives a name like this. But it just will make it sharper. So you remove the smooth component, will basically emphasize the edges more, so it looks like it's sharper. And this the entire image should be like this. I'm not sure you can see that carefully. Clearly there. So let's look at another example. So this example, I guess some of you guys did it in the homework. I asked for a grayscale, but you guys do black and white, and of course you guys are okay. I good. So because I say black and white, and you really give me black and white. So some of you guys did the thresholding for your videos. So and this gives you a black and white apparently. So it's just when the intensity is bigger than, in this case, bigger than 100, you just set it to like the brightest intensity. So set it to 255. So otherwise you just set it to 0. So you have kind of like result like this. So okay, my question here is like, is this linear operation? Just want to make sure. Sure. Think of the definition of linearity. Yeah, there's a hint that like probably not linear. Can you show that, like just give a counterexample that it show that it's not linear? So remember, like for linear, it should satisfy something like this, like alpha G and M is equal to alpha S G and M. So just consider a pixel. If I have intensity like equal to 60, let's say, and I set alpha equal to 2, right? So on this side, what do I get? On this side, we get S120, right? S120 will be 255 because it's bigger than 100. Right? So this is bigger than 100, so therefore this is equal to 255. But if I look at the other side here, S60 is less than 100, right? So therefore this is equal to 0. 0 times 2 is still equal to 0. So therefore this is not equal. Yeah. And so this operation is not linear. So
So we're looking at it like as a pixel-wise, you're not looking like, I don't know, okay.
Yes, yeah, but yes, yes, it's pixel-wise. Here is pixel-wise. Yes. So another property, if you study kind of cell processing, you may heard of that or remember that, like shift invariance. So the idea is very simple. It's just if you have an image and you operate that, and it would be the same as you. Okay, I should say an image, I operate that, and I shift that. It will be the same as if I first shift that and then operate that. I should get the same result. Other way to think of that is basically I have an image. If it's shift invariant, actually I'm jumping ahead. And if if your operation can be represented using a filter, like something like a dot product we just mentioned, like is equal to operating on a pixel will be equal to dot product of the neighborhood of that pixel with a filter, then the operator is shift invariance only if like your patch, that filter has to be equal everywhere. Like it kind of makes sense, right? If it's not equal everywhere, for example, like if I have the filter like here is not the same as here, then originally I operate here, I will use this filter, right? If I shift to here, I'm using another filter, then of course I will have a different result afterward. So does it make sense? Yeah. So then this is just a verifying some understanding here. So if I have a box filter is essentially just a moving average, basically, that we have at the beginning. That will be a shift invariance. We can easily verify that, right? So just by the definition, if I shift the input a little bit and I operate that, so essentially I shift by n log and m log, and I operate that, what I get is equal to this guy here, right? So because I have n and n changed to m minus n log and m minus m log, and of course this is just equal to, by definition, it's just equal to this guy. Also, don't worry about that. If you think of that, like if I look at that, actually it's more confusing than you just think of that. For me, like this is but as I said, like you can just think of like your filter is essentially the same everywhere, right? So no matter where you move that, it's still the same. So therefore, whether you first shift to here and operate will still be the same as you not shift and operate here and then shift later on, right? So if the filter is not the same like here and there, then you cannot have this property, right? So this is shift invariant. So actually, like a important that's we mentioned that like Faso is not a linear system. It's not linear. This is just box filter is linear. Actually, okay. So then actually what we just described earlier is actually a more formal terminology to describe what we talked about earlier. This dot product, this neighborhood with a filter is actually called a correlation. So it's like you have a filter that in this case I sometimes people call it a kernel as well. Like I have this edge here, so I have that patch, it's just a neighborhood, or just like do a dot product and get that pixel. So now I'm making you guys confused a little bit in the next line. So this is correlation, but actually if you're in signal processing, and we have this correlation, I have a symbol like this, correlation. And signal processing is very common to talk about convolution. You guys remember that, like we talk about convolution in signal processing. You see the definition a little bit different. When you have like correlation, this have a plus side here. This is an addition here. But if we are talking about convolution, there's a minus sign here. It looks a little bit more confusing. But we can relate convolution with correlation somehow, because with some change of variable, for example, like I can define h flip, just like I flip that particular image or kernel. If I flip that, then the index will be like from uv will become like minus u and minus v, right? Now if I change this to minus u minus v, then I can, instead of something from like minus k to k, I basically I just change a variable, right? I can just call this minus u as like u pi, or like minus v equal to v pi. So essentially this is just the same as here. So therefore it's actually this convolution is just equal to the h flip kind of correlated with f. So it's nothing really mysterious. So then you will say like, why? Okay, anyone feel a little bit like annoyed by this? Like, why we need to have convolution? It looks like correlation is much more lateral, right? So it's like you have a patch and then you do a dot product and that's it, right? Why we want to flip it somehow is kind of like weird, right? So so this a little bit annoying. It's coming from a little bit signal processing, if you remember. So why we have that? Like think of 1D signal there. Like let's say if I have like think of this as I am having like a system getting some so-called impulse response. Let's say if I hit a drum or something, like if I hit a drum, then it's kind of like have a signal. This, of course, this is not a kind of reasonable signal, kind of hitting a drum. Like maybe I have signal like that, like coming out, like when I hit that. So then like I want to ask like what will be my signal, maybe at this point here, maybe at this point here. So maybe I hit the drum like at this time like at 0.5 seconds and also like at 1 second here. So then like I hit the drum, then of course like here I will have some response will go to like this way, and this I will have another response like this way. So basically my signal at this point will be equal to like the signal here due to like hitting a drum at time equal to 1 plus here hitting a drum at time equal to 0.5. So then this will be equal to what? Equal to a like 0.5 times h. So let's say I have 1.5 here, or I just write t. And I see like how much I decay will be equal to this minus this will be t minus 0.5, right? And plus like at here like a1 h t minus 1. So you see that like this is where we get this minus sign coming from. So actually therefore like the convolutional things like come up very laterally when you are processing 1D signal basically. If you have 1D signal, you look at the impulse response and look at the time, and particular time will be just like get you that. So so then besides the influence by like DSP, another why we are kind of interested in convolution is like actually has nice word property. I see that you guys are getting a little bit kind of bored. I'm not sure bored or like anyway. So but I won't just get into tiny detail out of this, but I just kind of like run through this. So I think it's good to know because it's kind of like sometimes you need some of this theoretical knowledge, like just give you intuitive. So whether this makes sense or not. Typically, the fastest way to realize someone is BS-ing is like from some of this theory knowledge. Like you don't even need to verify. And I actually watched another video like yesterday, like YouTube, about like a guy. I don't know whether you guys know that Schwarz. I don't know, like he's a machine learning guy. Yes, and then like that's. He got lots of like hate recently because he made up a course and then I think you know that, probably just you know that. But there's something like he also plagiarized like someone else's paper as his own, and even worse is like he don't actually understand many of the stuffs. Then he for example he makes Gaussian logic gate. I forgot like something like I don't know what logic gate or something like. He tried to not plagiarize completely, so then he changed gate to door, something logic door, and stuff like that. So therefore, like I mean, it's like sometimes like being practical is nice, but this theoretical stuff at least is good to know, so that you don't make yourself a total kind of like idiot. So when times come, basically. I won't go through that because you can read this. It's very simple. So it's very easy to verify if you have like convolution. Actually, it's commutative. What do we mean by commutative? Is like you have an operation like H convolve with F is the same as F convolve with H. Of course, here I'm ignoring the boundary condition here. So this is very nice. And know that like it's not true for correlation always. It doesn't necessarily that like when you change the order, it will be the same. And also, so yeah, we have so-called this associative property. If you have like, for example, G, H like two filters, like as our first example there, remember like we not the first couple example, we have that filters. I forgot like something like 1, 2, 1, minus 1, minus 2, minus 1, right? So we can think of this as like a filter like decomposed into 1, 2, 1 and minus 1, 0, 1, stuff like that. So then like the associative property is saying that like you can first like combine these two together. So these two guys convolve, you get that these things, and then you apply this image on this filter will be the same as you first kind of apply to this filter and then apply to this filter. So, and you can also like just go for this very simple math, verify that like, of course again I'm kind of ignoring the boundary conditions there. So, but if you ignore the boundary condition, just look at the center of the image basically, then you have the associative property. Again, like correlation does not satisfy that in general. So this I will jump through that also because I use that in the next slide, but you can easily verify that like if I have like A convolve with B, if I flip the order, it will be just equal to A flip and convolve with B flip. So again, so I mentioned all this property here. I just use that A convolve with B flip is equal to A flip convolve with B flip because I want to show that like associative is not true for like correlation. So for correlation, for example, like if I look at this like A correlated with B correlated with C, then this is equal to B flip convolve with C, right? And then like this guy will be equal to A flip convolve with B flip convolve with C. And all this is associative, so therefore like I can change the bracket here also, or like I can remove the bracket because convolution is associative. But on the other hand, if I do this first, like A correlated with B first, then with A flip convolve with B, and then this correlate with C is like A flip convolve with B flip and then convolve with C, and then this one I didn't show, but I just say that like you believe me, this is very simple math. Like in the last line, this is equal to A flip that is just A convolve with like B flip, so therefore equal to this. So these two is not the same, so therefore I say correlation is not associative. So you can also show them distributed law like for whatever. So I won't bore you with that. But it's good to know that like convolution have some nice property. And so when you play with, for example, like most importantly, when you have a filter, you're doing correlation, do not automatically assume something like this, like you can change the order and so on. It's just in general not true. But I want to say, in image processing, often it doesn't matter as well, because in image processing, at least if you don't do convolutional neural network, even for in most of the time your filter will be symmetric. So apparently, because like where am I? I hope I cannot find it actually. But you remember that like I just went through that actually. Where is that? Oh, here, I'm sorry. So when I do convolution, it's equal to, if I H convolve with F, it's basically equal to H flip correlate with F, right? So therefore, like the difference will be just like I flip the kernel, right? So therefore, if the kernel itself is symmetric, the two operations will be the same. So in often, for example, you do some filtering, it's like often you have these kernels are the same, so therefore like, it's symmetric, so therefore like these two operations are actually the same. Yeah. So I see it. Yeah. Okay, and let's see what else. If I go back to here. Oh, this is actually a nice knowledge to know, but I won't give a proof. It's basically if you have a shift invariant filter, so then you can kind of show that actually you can show that like if you have a linear shift invariant filter, you can always represent that as a convolution. So you can always show that like that filter is actually can be represented as just you can represent as convolution, then also it can be represented as correlation. So can always represent as like you have the target pixel, the output of that target pixel is just equal to the label of that pixel dot product with some patches. And that's actually, with this theorem, I can safely show the stability property like I described at first page. But of course, I also like here, I need to add an additional condition if this is the filter is shift invariance also. Like if it's linear and also shift invariance, I from this theorem that basically is stable as well. Yeah. So let's see. I guess I will do something. I guess this you guys asked me earlier is like for the boundary we can put patches. I'll just skip here. Like typically you can do a zero padding, or like you can do a mirror extension, blah blah blah, so this is just a summary slide that like so just in practice, when people say convolution, they sometimes actually mean correlation, but be careful. Like when the kernel is not symmetric, they are not the same. So we can be sloppy because often the kernel is actually not the same. Yeah, the kernel is symmetric. And if the kernel is not symmetric, then you need to be really careful that like lots of these properties, for example, associative, commutative is not true. So for correlation, and actually because like these kernels are so often symmetric, actually in OpenCV they didn't even implement actually convolution, they implement correlation. So therefore, if you really actually want to implement convolution in OpenCV, be careful that you need to flip the kernels. So you need to flip the kernels before using that. And And of course, if the kernel is symmetric, then you don't care. So we have this box filter to begin with that doesn't look very good. So this is a improved version. This is have a Gaussian kernel. So it's very simple. Right? We just have this bell shape of filter patch. With this, then like actually the result is, if you remember, it doesn't have that artifact. So we have this moving that out, but also doesn't have the artifact. We will have kind of better explanation why we have this artifact when we look at the Fourier transform of that, maybe later on. Earlier when we have the box filter. And so, oh yeah, this is like just an immediate comparison. I guess you can see that like when we use the box filter, this has this series like kind of like grid artifact there. Gaussian filter, yeah. Another nice property for Gaussian filter is that actually it's separable. So you can split into this function like gxy as just x and just y. So it's similar to like if you write this as a kind of patch, it's similar to the other example we just gave. That's like 1 minus 2. Oh, sorry. 1 2 1 and 1 0 minus 1 again. It's similar to this guy. It's that like your patch can be decomposed into like kind of row multiplied by column multiplied by row, or row, yeah. And then like you can therefore operate first like in the kind of like line by kind of row by row first, and then operate column by column. And actually, if you count the number of operations, doing this will be like more computationally kind of efficient than like you kind of compute the filter like at one time. Basically, like this will give you a kind of linear of n instead of n squared if the kernel size is n. But of course, it's not actually that important if your n is not big. When your kernel is not that big, it's like maybe 3 by 3, maybe. But it's still like you can gain something basically. It's just an example that separable. So we mentioned, okay, we quickly show this Gaussian filter. Let's look at another filter. This is a medium filter. A medium filter will be like, you have a patch here. Again, we look at the neighborhood of like a target pixel. So in this like box filter, we just take an average, right? But the median filter will be like, I'll compute the median of this guy. Do you know what is the median? Like, yeah, something like, yeah. For example, if I have like if my values here, maybe I have 2, 3, I make a, I don't know, 1, 2, 9, 4, 5, 1. What's the median for this patch? What, you're that quick? Yeah, it could be actually. No, wait. So, be very careful. Yeah, I think you are very close. I'm not sure it's 2. Yeah, you too. Yeah, you're right. So we should look at, basically we should just sort the pixels here. So it's like the value is 1, 1, 1, 2, 2, 3, 4, 5, 9, right? So the median will be the middles. So it will be 2 there. So median filter is very useful to remove this so-called salt and pepper noise. So like this guy here, if I use median filter, this is if do a box filter like 3 by 3, that one, it doesn't do very well. So but if I have a median, okay, this is like, okay, not median filter yet, but it's like a even larger box filter. So if I use a median filter like 3 by 3, this is like can remove that very efficiently. So let's me So we mentioned the unsharp masking, like that's basically like early on. Remember we have an image, subtract the smoother version to get a little bit more kind of like a sharper image. And this, as you see, like typically this operation have a disadvantage. You will get some halo like around those edges. There's another filter that relatively recent. I forgot like when people invented that, like maybe a couple decade or something ago. It's so-called bilateral filter. It will kind of like try to preserve the edges somehow. So basically, like the idea. So I will just give a quick. Quick explanation of this bilateral filter. The idea is very simple. So basically, if you think of like I do a filter, like for example, a Gaussian filter, what I did is I just try to take average of the neighborhood somehow, a weighted average of the neighborhood. But I basically ignore the actual pixel values there. So my kernel will not depends on, like for example, like I have a kernel like this. My kernel here will not depend on my input. It won't adapt to my input. So the idea of the bilateral filter is like I want to adapt to the input somehow. So for example, if I'm doing a smoothing here, I want to adapt to the edges. For example, if I know this is edges, so I don't want to kind of mix up like this part and this part. So I don't want to, like for example, if I compute the average here, or like I compute the enhancement at this particular pixel here, I want to ignore the part here because this is like kind of like probably like it's not in the same boundary, I would say, right? So this will fall into, this pixel will be more fall into this side here. If I use the information here, I'm going to kind of just get some what should I say? Undesirable blurring somehow. So the idea is very simple. So how they do that is basically I change the kernel here and make the kernel kind of adaptive to your pixel value as well. So basically they added like an additional part for the kernel. It's like if your current pixel value is too far away, I mean, if I'm going to, for example, I take average of each of this guy, right? So if this value is too far away from this target pixel, I'll just ignore those. So if it's close to mine, then I will include that. So therefore, I will adapt this kernel here. Therefore, like instead of a kernel like this part will mostly go to COC or something like this. So very simple, it's a very simple idea. So in practice, we basically just look at the difference between these two values, right? And then just do a kind of what should I say? Do a distance measure between those. So this distance measure typically is just a Gaussian like kernel like that. So if it's like this is another Gaussian function here. So if I have these two are close together, so it will be somewhere here. If I have this other value is like far away, then I will have value here. So very simple. So and so this is like exactly what I talk about. So originally the kernel is like this. So in this area the kernel will be like keep like this, right? But in here it will adapt to the values in the neighborhood. So this is far away from this center pixel here. So therefore like this I won't take that for the average. So and then like you will get a little bit better results. So okay, okay. Actually I spent more time than I expected. Finally, I want to say one more thing is like doing histogram. All of you guys know histogram already, I guess. So it's just like I take a pixel, I take a patch here, and I just order the values in terms of intensity, and I want to get a empirical distribution of those values, that will be known as a histogram. So for example, like for this patch here, you have like this intensity is highest. Basically, I don't know what, probably this is the skin here, have like high, and then like with pretty high intensity here, probably is the hair here. Maybe here have a little bit here, probably is the white region here. So now I want to mention the histogram is like one operation that I want to explain is so-called histogram equalization. In practice, it's very simple and but pretty useful. So for example, like if your image or like you capture from a camera is somehow does not efficiently using the entire range of the intensity, like this one here. So what you can do is that you try to kind of adjust each of the pixel values so that like it will utilize the entire kind of intensity efficiently. So and you will have a equalization like this. So essentially, that if you look at the histogram, original histogram like this, and you look at the cumulative density function for this histogram, so basically just adding this intensity, continue adding this intensity until this together. So and I want to change this CDF into something like linearly like this, so then it will utilize everything. And so if I do that, then I will have this nice result here. I guess it's okay. I won't go into detail like these steps here. First is I think like as long as you know what this is going on, you can figure it out yourself. Second is like in OpenCV, it's just one command. You don't need actually to do.
CDF stands for what did you say?
Yes, sorry. The CDF is basically the cumulative distributive function that is just like adding. It's just a Q-sum operation of these guys. So for example, here you're starting to have some values, right? So I have this histogram here. Maybe I put an example. So for example, I have the histogram is like this, just 4 values. So it's like 50 or like 150, 160, 160, and 190. So I have 150 here, 160 here, 190 here. So I have like 1 here, 2 here, 1 here. Then the CDF will be something like I have 150, have 1 here. Then 160, I will add this and this, add this and this together. Then I have 3 here. And the 190, I have like this, add 1 here. So I have 4 here. Just the cumulative. Okay. Yeah. So therefore, like I want to somehow this change to somewhere this way. So then, like actually, I can continue with this example. From this to here, then what you can do is say I want to make. So this is equal to about 1/4 of this region, right? So therefore, like this, I should map to like 255 times 1/4, right? Then it will be nice. And this map to 255 times what's that? 3/4. Yeah. And then the last one. So I can do an operation. For example, this will change to like 255. This is 255 by 3/4. This is 255 over 4. Then it should have an effect of like the histogram equalization. So, okay, that's the end.
Which filter was the one before this one?
Oh, the bilateral filter. This one, is that you're talking about?
Bilateral?
Yeah. Actually, I was prepared to thinking to do some demo, but seems like let's see if I can.
Well, when you try to take a photo or video at night and your camera doesn't have good night vision, it it's real noisy like that. Would that work on those kind of videos or images?
You can, but probably but very careful. Like this actually visually give you better result, the histogram equalization. But if you use that like for further processing, it may not have any gain. Because if you think of like you don't actually have more information. You just look better. Does it make sense? Yeah, visually it's so better. But if you have like some, of course, it's hard to say because if human perception is quite amazing. Like here, maybe it's hard for me to say anything after changing this. Supposing there's no additional information, but probably I can process this more efficiently.
But a computer would have no
But
problem.
yeah, but computer may have problem. So because for the computer, it will be like the same thing to them. Like you don't actually have additional information there. So you may or may not have gain. Actually, in theory, you shouldn't have gain.
Well, actually, it depends on what you set your thresholds to be.
Yeah. I think this is be careful. This one doesn't have threshold. When you do the equalization, you just make it uniformly like just stretch that. But what I'm saying, like, you don't actually automatically gain some more information doing this operation. But for humans, it's kind of amazing. Like, I probably can process this white images better than this left one. But depends on like what you're going to do like later on. It may not have gain.
If you're going in and out of fog with image processing,
Yeah.
or maybe in and out of smoke, and you didn't want to have dynamic thresholds, then you would want to do something like that, right?
You can, but also one thing, be careful though. Like you may have this intensity keep changing, the mean will
Yeah, that's
change.
an ideal situation.
Yeah, that will change
Yeah.
because you will change the mean when you do that. If you're, of course, you can do lots of stuff. Like if you have multiple images, like if you have a video stream, then like you have multiple frames, then yeah, there's lots of things you can consider actually. So I guess I will stop here. So maybe like next time I can just do some quick demo of what I talk about today, and then we'll talk about something else.
Are you going to be posting your lectures?
Huh? Sometimes, yeah. I
Where? I haven't seen it.
lecture. Oh, I link to my website as lecture.
PowerPoints.
Yeah, PowerPoints. And sometimes if I remember, there's a video there. Sometimes if I don't remember, yeah. This time I remember, I can put up a video.